In this video, we will learn about theory portion of topic 12.7, that is curvilinear motion, normal and tangent coordinate system. In the previous video, we have learned how to calculate position, velocity, and acceleration of the particle if one of this is given as a function of time or the information is presented in the graphical format. That coordinate system that we have applied to previous sections is called the Cartesian coordinate system, or XYZ, where we calculated x, y, or z coordinates of position, velocity, and acceleration based on the given information. This Cartesian coordinate system is very useful when the particle has a straight line motion or it's going through a curved path. But for Cartesian coordinate system, we measured all position, velocity, and acceleration relative to our fixed origin, which is 0, 0, 0, and the distance and velocity and accelerations are measured in terms of x, y, and z coordinates. What we are going to learn in this video is we will learn different types of coordinate system that is called normal, tangent, and binomial coordinate system. And there is for remainder of the chapter 12, we will study about cylindrical coordinate system and polar coordinate system. So these are different coordinate systems depending on the application or depending on the on how the motion of the particle has been given. We will use one of this coordinate system. Normal, tangent, cylindrical, and polar coordinate system are typically useful when the particle has the motion along a curved path. For all this coordinate system, our ultimate goal is to calculate position, velocity, and acceleration for the given particle. So topic 12.7 is about normal, tangent, and binomial coordinate system. Objective: determine the normal and tangential component of velocity and acceleration of a particle traveling along a curved path. For example, this box, when it goes on this conveyor, it travels along the curved path, and at any given instant, if we would like to know the velocity and acceleration of the particle, we can use normal tangent coordinate system. Now, normal tangent is typically a two-dimension coordinate system. That means the particle has motion only in one plane. But if the particle has 3D motion, then we use normal, tangent, and binomial coordinate system, which is equivalent to x, y, and z axis. If a particle travels along a curved path with a constant speed, then the tangential component of the acceleration is 0. The normal component of acceleration presents the time rate of change in the magnitude of the velocity, time rate of change in the direction of the velocity, magnitude of the velocity, or the direction of the total acceleration, and the correct answer is B. It depends on the direction or change of the velocity. Anyways, we'll learn about this answers through the presentation. So let's look at this example. Now, we know that velocity is a vector. That means velocity has both magnitude and direction. Acceleration is time rate of change of velocity. So with reference to that, let's look at this example that a car is speeding up in a straight line, experiences acceleration due to change in magnitude of velocity. So here car goes in straight line, that means the direction of the car does not change. What changes for V is only the magnitude because it speeds up. So this type of acceleration is called the tangential acceleration, which is because of change in magnitude of velocity. Now let's look at another example that the same car is now traveling along a curved path at constant speed. So if the speed is constant, then there is no change in magnitude of the speed, and that means the acceleration is 0, but it's only the one component of acceleration that is 0, called tangential component. However, because the car is traveling along a curved path, there is a change in direction of the velocity. So velocity at any given point along this curved path is tangent to the path at that point and points in the direction of motion. So if the car is here, then this is the velocity of the car. If car goes here at some point, velocity is tangent to that point and it points in the direction of travel. So this is the velocity of the car. If car reaches here, then it's tangent and again points in the direction. This is the velocity of the car. So we can see that every instant the velocity direction changes, not the magnitude. And the car experiences acceleration, and that acceleration is called normal acceleration, which is indicated by this arrow. So normal acceleration always points towards the center of curvature. So car is traveling along this curved path, and this point O is the center of curvature. So this is called normal acceleration, and for that we use the nomenclature A and subscript small n. N stands for normal. Similar to that, this acceleration is called AT, which is tangent. T stands for tangential acceleration. Now, what happens when there are both components of the acceleration present? For example, the same car traveling along the curved path, but not at constant speed. It's actually speeding up. So it's changing the direction as well as magnitude of velocity. So there are two components of acceleration. AT, tangential component of the acceleration shown by this arrow at the given instant, and normal component of the acceleration is given by another arrow, and it's always pointing towards center. So total acceleration of the car is combination vector addition of tangential and normal acceleration, and which can be shown graphically by this arrow, red arrow here. So A is the total acceleration, AT is the tangential acceleration, and AN is the normal acceleration. Now, normal acceleration at any given point, normal acceleration always points towards center, but the direction of tangential acceleration can be in the direction of motion of the car, or it can be in the opposite direction depending on whether the car is speeding up or slowing down. If the car is speeding up along curved path, then this is the right direction of the acceleration for tangential component. But if car is slowing down, then tangential acceleration points in the opposite direction. And there are different applications of there are many practical applications of normal and tangential acceleration. For example, car traveling along this clover leaf experiences acceleration due to change in magnitude of the velocity as well as the direction of the velocity, and this is called the total acceleration. How can we determine the total acceleration in this case? And why would we care about the total acceleration of the car? We should care about that because ultimately, if that acceleration is too high, car may lose the contact with the clover leaf and it can actually skid out of the circular track. In this example, a boy is swinging on the swing, so experiences both tangential and normal component of the accelerations, and we can calculate the total acceleration of the boy by combining AT and AN parts of the acceleration. Roller coaster car going from point A to point B along this curved path experiences both tangential and normal component of the acceleration, because as it comes down it's speeding up. So tangential acceleration is in this direction and normal acceleration is towards the center of the curvature, and together the total acceleration is combination of normal and tangential acceleration. And why would we want to know these values? Because we would like to limit the value of acceleration for the passengers, because humans can withstand only certain maximum value of acceleration such as 3 to 4g acceleration, where g is the gravitational acceleration, that is 3 to 4 times gravitational acceleration for only limited seconds. So if the acceleration value is too high for too long, it can result in person getting faint, or that person, like, it can have adverse effects on the body of the human. So let's look at the normal tangent coordinate system. Particle is traveling along the curved path, so we use new coordinate system. So instead of xyz, we will call this coordinate system ut, which is unit vector, or sorry, we call this coordinate system t for tangential, N for normal, and B for binormal. So first step is, for any given position of the particle, define the tangential axis, which is t, define the normal axis, which is always towards the center. Now ut and un are unit vectors for tangential and normal axis respectively. These are equivalent to using ij values for x and y. So instead of ij unit vector for xy, now we will use unit vectors ut and un for tangential and normal coordinates. Okay, so yeah, you can see that here unit vectors ut and un are for the unit vectors for tangential and normal axis. So total acceleration of the car or a particle is combination of tangential and normal acceleration. So here at is the magnitude of the tangential acceleration, ut is the direction of the tangential acceleration, an is the magnitude of the normal acceleration, and un is the direction vector for the normal acceleration or normal coordinate axis. At can be calculated using v dot. V dot stands for dv by dt. For engineering dynamics and mechanics, whenever we put one dot on top of a variable, one period, that means it's one derivative or first derivative of that variable relative to time. So v dot is dv by dt. If you write s dot, it is considered as ds by dt and so on. And this is the equation for tangential acceleration. And for normal acceleration, we have this formula an is equal to v square divided by radius of curvature. So at any given point, the normal acceleration of the particle is the velocity of the particle at that point, and square of that divided by the radius of curvature, which is nothing but the distance of particle from the center of rotation at the given instant. Remember that this velocity and acceleration calculations are instantaneous calculations, means only for the given instant. And total acceleration can be calculated as a vector as shown here by this equation, and its magnitude can be calculated same as the magnitude of the vector, which is square root of normal component square plus tangential component square. Now there is a special case that when radius of curvature rho is not clearly defined, instead the curved path is defined y as a function of x. For example, x is horizontal axis, y is vertical axis, and any point along this curvature can be calculated using y equal to 1 by 100 x square. Means when x is 0, y is 0, which is this point, and when x changes, value of y can be calculated as per this equation. So particular value of x, y is here. Now for this type of problem, well, y is given as a function of x, radius of curvature cannot be directly calculated. At that time, we can calculate radius of curvature using this equation. And when it's a three-dimension coordinate system, then along with normal and tangential, we also have binormal axis, which is, we use nomenclature B for that. So T for tangential, N for normal, and B for binormal. However, for three-dimension, for normal tangent binormal coordinate system, particle has motion only in normal tangent plane. It does not have any motion along binormal plane. That's what we assume for now. So particle does not have 3D curvature motion, but it has only 2D motion in normal tangent plane. Now we are going to see a few examples of how to calculate normal and tangential acceleration in the next video.